is to start and end patient testing with a QC evaluation. So we should evaluate in batches. What does that then mean? Our QC procedure should directly reflect how many patient samples we are running per day. So again, it would make sense maybe to run QC after every 50, after every 100 patient samples, something like that. We should start and end every day with a QC evaluation. Ultimately, that is going to save us money in the long run. So if your lab runs in 24-hour operation, make the time between QC evaluations shorter than the time needed to correct erroneous results. So this is something that we say a lot, basically because it is an ISO requirement that if, say, at the start of the day, you run your QC and it passes, everything's fine, you then run 100 patient samples, and at the end of the day, you run your QC and it fails, you then have to rerun all 100 of those samples. And that is standard procedure in the UK. So in the UK, they want to make sure that they don't have to rerun 100 patient samples, because that would be a lot of work. So they may run QC every 50 patient samples, every 20 patient samples. It's up to them. Generally, people will be quite conservative with the amount of QC they run, because QC costs money, and you know it's not cheap, it's not free. But obviously, it's important to remember that if you do try to save a little bit of money by not running enough QC, you run the risk of having to repeat a lot of work, which obviously is going to cost you a lot more money and time in the long run. So ensure you know the number of patient results between your QC evaluations, because that can help you develop a much more advanced QC strategy. So when deciding QC frequency, the QC frequency must be based on the performance requirements of an assay, the number of patient samples, and the time between QC evaluations. So this is what's termed taking an holistic approach to QC management, so considering a lot of different factors before we say, okay, we're going to run QC 3 times per day, we're going to run QC 1 time per day, we're going to run QC 5 times per day. These are all the things we need to think about before we can make that decision. So it's all about balance. So you can run to QC too much, which means obviously you're going to waste money, you're going to get more than likely more errors that maybe aren't significant, and the opposite is generally true where people don't run QC enough, and then they run the risk of releasing incorrect results, which can have huge ramifications for that lab. So let's think about a scenario where Lab A performs QC 1 time per day, and they run 100 tests per day. And Lab B performs QC at the end and start of a shift, and they run 100 patient samples per day. So if an error occurs in the test system after 50% of the samples have been run, what is then the consequence? That means more than likely Lab A will not detect that error until the next day, until the following day, whereas Lab B will detect that error at the end of their shift. So it means Lab B is in a much better position to put corrective actions in place and potentially to rerun those QC if necessary. So second scenario is where Lab C performs QC at the start and end of the day, and they run 100 tests per day. And Lab D performs QC at the start and end of the day, and they run 1,000 tests per day. Again, if an error occurs after 50% of the samples have been run, what are the consequences? Potentially Lab D may have to run 1,000 patient samples again. So these are quite extreme examples, but this does happen in real life, and any lab that is ISO accredited will have to rerun those patient samples if they respond to an error. So the idea here is to evaluate in batches. So for this lab that say was running 1,000 patient samples per day, it would maybe make sense for them to run QC after every 100 patient samples. That way, if they have an error, the maximum number of patient samples they will need to retest will be 100, which is still a lot, but it's nowhere near as much as rerunning 1,000 tests. So start and end every day with a QC evaluation as a minimum. Reduces your costs overall. So So the next thing we're going to consider is to know the characteristics of good QC results. So in order to recognize what a bad result is, we also need to recognize the qualities of a good result. So in an ideal world, the characteristics of good or normal QC results on a Levy-Jennings chart should fluctuate randomly around the mean for comparison. There should be about an equal number of results above the mean as below the mean. So an equal number of positive and negative results. Your results should very rarely exceed 3 standard deviations. So approximately 3 in every 1,000 results should be outside 3SD in terms of statistical probability. On occasion, your results should exceed 2SD. So it's normal for 1 in 20 results to exceed 2SD. So it's normal for 5% of the time that your results are outside 2SD. And on the whole, your results should be within 1SD. So about 68% of your results should fall within 1 standard deviation of your mean. So this is a prime example of what a normal Levy-Jennings chart should look like. So results fluctuating pretty randomly above and below, with one result outside 2SD. So that result outside 2SD is not necessarily an error. It's not necessarily something we need to be overly concerned about, because it could just be a random error. So it's very, very important to keep those characteristics in mind. Otherwise, you run the risk of unnecessarily rerunning QC, unnecessarily troubleshooting QC, and potentially wasting a lot of time and money. So the most effective way to recognize QC errors is to use QC multi-rules, also known as Westgard rules. Secondly, we should be participating in an ISO 17043 accredited EQA scheme to help recognize any potential errors we might have. And we should also make sure that we estimate the magnitude and size of the out-of-control error before we correct it. So obviously, if it's just a minor error, we're not going to put a whole lot of, we're not going to invest a lot of time into troubleshooting that. Whereas if it seems to be a major error, we're going to spend a lot of time and resources making sure that we resolve that issue as quickly and effectively as possible. So, for example, very, very standard laboratory rules that nearly every lab in the world uses is one result outside 2SD, reject, or one result outside 3SD, reject. So those are the most common rules that are used in every lab. So the problem with those is it's prone to the, if you get one result outside 2SD, you repeat. If it's still outside 2SD, you maybe repeat again, and repeat again, and repeat again, until it comes back within range, and then you can say, okay, perfect, I'm good to go. So that's not necessarily the case. I think a lot of us in this room would be lying if we said we've never done that. I know I have. If we have one result outside 3SD, it's a little bit more significant. We rerun. If it's still within that range, then that means we've got potentially quite big problems. So what we want to do is use a QC multi-rule strategy. So this is a commonly accepted way of doing our QC multi-rules. So first of all, we have our control data that we generate when we run our control. So we look 1, 2S. So is that result outside of 2SD? Yes or no? So if it's not outside 2SD, our control is in control, passed, everything is fine. If that result is outside 2SD, we need to then move further down into our flow chart of QC multi-rules to determine whether or not this is an error. So firstly, is that result outside 3SD? If it is outside 3SD, it's an error. We need to reject the run. We need to start troubleshooting. If it's not outside 3SD, we then move on. So 2, 2S. So that is where 2 consecutive results are outside 2SD. So if you have a result that's outside 2SD, you repeat, and the next result is also outside 2SD, that means you've got an error. You need to reject the run and begin troubleshooting. If that's not the case, we move on. We then have, this should actually be R4S. So this is a slight typo on my part. What that means then is the range between two QC points, is it 4SD or greater? So that means, for instance, if you have one result that is plus 2 SD, the next result is minus 2 SD, that is a range of 4 SD. That would show that you have some kind of issue going on. So if that's the case, obviously we reject. If not, we move on to 4.1S. So that's where 4 consecutive QC results are outside 1 SD. So that would show you the beginnings of potentially a bias. If we then realize that that is not the case, we move on to 10x. So 10x is our 10 consecutive QC results on the same side of the mean, either positive or negative. So that can detect any kind of drift or any kind of bias over a slightly longer period of time. So also we should participate in an accredited EQA scheme. So EQA is one of the best ways of detecting particularly calibration errors in your lab. So if you have a calibration error, quite a deep-seated one, generally that is not picked up by your day-to-day QC. So your day-to-day QC performance will look okay, whereas then you'll run your EQA and you will say, okay, my performance has failed. Why is this? Chances are it's because of some kind of calibration issue that's quite hard to detect. So that's why it's important to use a very robust EQA scheme to help identify those. So it gives you a good perception of your accuracy, and it gives you added confidence that you're releasing accurate patient results. So here we have a case study of a lab that came to us and said that they were querying that their IQC was perfect for sodium on their chemistry QC, but they said that they had a constant negative bias on their RICUS scheme, which is our own EQA scheme. Stands for the Randox